Today I'm going to explain the theory of relativity using Minecraft. But first of all, there are two types of relativity: special relativity and general relativity. Let's start with special relativity. It all begins at the start of the 20th century, specifically in 1905, when Einstein introduced special relativity. This theory transformed our understanding of time and space, proposing physics laws are identical for non-accelerating observers, and light speed is constant for all, regardless of motion. From this theory, surprising ideas emerged, such as time dilation, length contraction, and the equivalence between mass and energy. Next, I'll explain in more detail with some examples. Wait a moment, if you're enjoying the video, subscribe, as only 0.4% of viewers are subscribed. Please do it. Just hit that red subscribe button to help me grow this month. Okay, let's continue with the video. Imagine you're on a train that's moving very fast. You have a ball that you throw up and then it falls into your hands. From your perspective, the ball goes up and down in a straight line. However, if someone is watching from outside the train, they would see the ball move in an arc due to the train's motion. Despite these different perspectives, the laws of physics, the laws like gravity, which makes the ball fall, work the same for you inside the train and for people outside the train. You could say that ball traveled in time to the future. It was also observed in astronaut Sergei Krikalev, a Russian cosmonaut who spent a total of 803 days, 9 hours and 39 minutes in space throughout his 6 missions. And due to the effects of time dilation, Krikalev technically traveled to the future compared to people on Earth. This theory is surprising, showing how we can travel to the future by moving at near light speed. Now I'll explain these concepts, starting with what is time dilation? It's a phenomenon where time doesn't pass the same way for everyone, but rather depends on their state of motion and position within a gravitational field. Well, in simpler terms, it means if someone moves at speeds close to light or is in a place with very intense gravity, they'll perceive time differently than someone at rest or in a weaker gravitational field. Now let's discuss length contraction. This means an object moving near light speed appears shorter in its direction of motion from a stationary observer's viewpoint. This contraction is only significant at relativistic speeds, since in our daily lives it's imperceptible. But how does it work? Imagine you have a spaceship that is 10 meters long. If this vessel travels at a speed approaching that of light, a stationary observer would perceive it as being much smaller. And then there's Einstein's famous equation. Energy equals the object's mass multiplied by the speed of light squared. This demonstrates that mass and energy are truly interchangeable. This means that a very small amount of mass can be converted into a very large amount of energy. And the reverse is also true. For example, in the context of nuclear reactions, we see that mass is directly converted into energy. These fundamental concepts have been thoroughly proven in numerous experiments and are absolutely essential for modern technologies like GPS, which must correct for time dilation to provide highly precise locations. Now it's here, we're going to talk about general relativity. Years passed, and in 1915, Einstein presented general relativity. But what exactly is general relativity? General relativity is nothing more and nothing less than an extension of special relativity. It's a theory explaining gravity in a completely new way. I have a video on gravity if you'd like to see. Instead of a force between masses, general relativity describes gravity as a curvature in space-time. I'll explain more. Imagine an elastic fabric. If you place a heavy ball in the center, the fabric deforms. Similarly, this happens with massive objects like planets and stars that curve space-time around them. But objects also move following paths called geodesics. In this curved space-time, Einstein proposed no difference between gravitational field effects and acceleration. For instance, if you're in an elevator accelerating upwards, you'll feel a force like gravity. Black holes are an example of general relativity. When mass concentrates in a small space, it can create such extreme curvature that not even light can escape. General relativity has also been confirmed by numerous experiments and observations. It has revolutionized our understanding of the universe, explaining phenomena like cosmic expansion and the existence of black holes.